Let's go back and try to add some more information now to our path. What I have written down here is all the information that we needed to solve the problem. But just for the practice, let's try to add some more information so that we can get more comfortable with kinematics. For example, remember that we really didn't have to pay attention to the peak in order to get this problem right. So I didn't write down anything that was happening at the peak. But just for the practice now, let's try to write down what's happening at the peak. All right, so we know that on the upward journey, the velocity is up and the acceleration is down. And on the downward journey, the velocity is down and the acceleration is down. Let's try writing up here, what can we say about the velocity and the acceleration at the peak? Pause the video and write down what we can say about the velocity and the acceleration at the peak of the path. Well, I hope it was clear to you that the velocity will be 0 at the peak. That's an idea we reviewed a couple times. At the peak, you're changing directions. Your vertical velocity has to be 0. And the acceleration should have been easy because the acceleration for vertical projectile motion is constant. It's always 9.8 meters per second squared down. So at this point, the acceleration was 9.8 meters per second squared down. On the downward path, the acceleration was 9.8 meters per second squared down. And at the peak, the acceleration is still 9.8 meters per second squared down. So even at the peak, the acceleration is always going to be the same. But the velocity can sometimes be going up on the upward path, down on the downward path, or 0 when we're changing direction. Once again, we see that the acceleration does not tell you which way you're moving. At this point, we were moving up, but accelerating down. And at this point, we were motionless for an instant, but we were still accelerating down. And you can see by the same token, the acceleration does not tell you which way the velocity is pointing. The velocity was pointing in up, down, and also the velocity here was 0. But those all were accompanied by an acceleration that was pointing down. I think I'm going to erase the work that we did for this problem now because I don't really want to think about this particular problem anymore. I just want to keep putting a little more information in about the path. Okay, so we know that at this point our velocity was 3 meters per second up. At this point our velocity was 0. We also know what our velocity was at this point now. Let's go ahead and label that. We know that at this point the velocity was negative 17.4 meters per second. We figured out that at the final point our velocity was negative 17.4 meters per second. And of course we knew at the peak the velocity was 0. And when we started, when we were thrown from the cliff, the velocity was positive 3 meters per second. How about, what was the velocity at this point? So we know that the object was thrown upwards from the cliff, and then eventually it started going down. What was the velocity of the object when it passed the cliff going down? What was the velocity of the object when it passed the same height of the cliff going down? Pause the video if you need to and give this some thought. You shouldn't need any equations to solve this question. You should be able to solve this conceptually with no equations. What was the velocity of the object? Remember, we're thinking about the same experiment where the object was thrown up from the cliff at 3 meters per second. It reached a peak, and then eventually it started falling down. Well, as it was moving down, eventually it got back to the same height that it started at. So what was the velocity of the object as it passed the point that it started at? What was the velocity of the object moving as it was going downwards when it reached the same height as the cliff? If you need to, pause the video and come up with an answer to that. I hope you were able to answer that conceptually without writing down any equations. We can use symmetry. Remember that projectile motion is symmetric. These 2 points are at the same height. These 2 points are at the same height, so they have to have the same speed. When we were originally on the 15-meter cliff, we were going at 3 meters per second. So when we get back to this 15-meter point, we should also be going at 3 meters per second. So the speed should be the same at these 2 points. At this point, the speed is 3 meters per second, and at this point, the speed is 3 meters per second. The velocity, though, also indicates your direction. Well, originally we were moving up, and now when we move past this point again, we're moving down. So on the downward path, our velocity would be negative 3 meters per second. So notice how we can answer that question based on symmetry without having to use any equations. It's important to have that intuition for projectile motion. So since we originally left the cliff at 3 meters per second, when we pass the same height going down, we'll be going at 3 meters per second again, but we'll be going at negative 3. So notice here, we started at positive 3, and then we were slowing down until the velocity reached 0. We were going at 3 meters per second up, and then gravity slowed us down until for an instant we were motionless with the velocity of 0, and then the gravity started pulling us downwards, and then at this point we started speeding up. So we went from a velocity of 0 to a velocity of 3 meters per second down, and then eventually by the time we hit the ground we were going at 17 meters per second down. So everything about what we have here on this path should be kind of common sense. We started moving upwards, gravity slowed us down until for an instant we were motionless, then gravity started speeding us up, moving down until we got back to our original speed. When did we get back to our original speed? When we got back to our original height, because projectile motion is symmetric. When did we get back to the original speed of 3 meters per second? When we got back to the original height of 15 meters above the ground. Projectile motion is symmetric. And then as we continued to fall down, gravity continued to speed us up until eventually we got to an even greater speed of 17.4 meters per second down. Remember that on the downward path, the acceleration is parallel to the velocity, which means that gravity is speeding us up. Whereas on the upwards path, the acceleration was anti-parallel to the velocity, so we were slowing down. Now, remember that all these little things that I'm figuring out now about this point and this point, these were not necessary for solving the original question that I asked you. In fact, they might have just distracted you from the original question. Remember, the original question was just asking what was the velocity when we hit the ground. Well, remember that to find the original velocity when we hit the ground, all we had to do was compare the initial and the final points. We did not have to think about the peak, and we did not have to think about this point on the downward path. But now I want to move on and just think about some other things that were not relevant to the original question, just for the practice for building up our intuition for projectile motion. So again, we're kind of forgetting about the original question and just figuring out more stuff about this path. Let me pose you another question about this path. Let's imagine now that we have somebody who's not standing on the cliff. We have somebody who's standing on the ground. Let's imagine we have somebody who's standing on the ground, and this person wants to toss an object up. And they want to toss the object up so that when it reaches the cliff, it'll be going at 3 meters per second. Here's a person standing on the ground, and they want to toss an object straight up so that when it reaches the cliff, it'll be going at 3 meters per second. So my question is, how fast do they have to toss the object up from the ground so that when it reaches the cliff, it's only going to be going 3 meters per second? So my question to you again is, if somebody is standing on the ground and they're planning on tossing an object upwards, well, they can toss it up as hard as they want. What initial speed does the person on the ground have to give the object so that by the time it reaches the cliff, it's going at 3 meters per second? Again, if a person is standing here on the ground and they want to toss an object up so that it's going at 3 meters per second when it reaches this height, with what original speed do they have to throw it from the ground? Pause the video and give that some thought. I hope you paused the video and gave that some thought. I hope you didn't need any equations for that problem. That was not an equation and calculation problem. That was a conceptual problem. How fast does the object have to be launched from the ground to reach 3 meters per second over here? Well, again, all we have to do is use the symmetry of projectile motion. The symmetry of projectile motion. We already know here that if the object was going 3 meters per second at this point, then when it hits the ground, it's going to be going 17.4 meters per second. 17.4 meters per second down. Well, now we're extending the path. Now we're imagining the object is starting from the ground. Well, then we're just going to take the 17.4 number and move it over here. The object would have to be thrown with a velocity of positive 17.4 meters per second. That was the answer to my question. The object should be thrown from the ground at a speed of positive 17.4 meters per second. We already know that, and we're just taking that from symmetry. We knew that when it hit the ground, it was going at 17.4 meters per second from having originally been going at 3 meters per second at this point and at this point. So the original speed over here, if we were starting at the ground, would also have to be 17.4 meters per second. So this, again, is an example of how we can use symmetry to solve the problem. By the way, this kind of gives a little bit of meaning to the positive square root to this problem. Remember that when we originally did the original problem, we took only the negative square root of 303. But now we can see there's a kind of meaning to the positive square root of 303. The positive square root of, at 303 is what the original speed would have to have been if the object had started it from the, on the ground. Well, I think we learned a lot of interesting points working through this last problem. There's a good chance that when you first did the problem, you might not have gotten it right, or even if you got it right, you might not have used the best approach or the best notation. So I encourage you, before you proceed, to just redo this last problem if you felt that you learned anything from it, or if you didn't use the best approach in attacking the problem.